Hi, Bruce here from S&S Cycle. Welcome to our second video on understanding cam specifications. In our first video, we showed you how a 4-stroke gasoline engine works and detailed the role of the valve train in the process. The valve train, of course, is controlled by the camshaft. If you haven't seen the first video, I'd highly recommend that you watch it before you view this one. You can do that right now just by clicking on this link. Still here? Okay, let's do this. We call this video the Big Three because we'll be explaining the three most important specifications to consider when selecting a camshaft for your engine. They are lift, duration, and intake closing time. It's not uncommon for riders to look at a chart of cam specifications and just choose the cam with the biggest numbers. Bigger is better, right? Chances are with that approach you'll spend a lot of money, but you won't be very happy with the results. After all, if it was that easy, we could just make one big nasty cam and call it a day. In reality, we make a range of cams for a range of applications. The cam you choose has to be right for your engine and, just as importantly, for your riding style. So let's get down to business and look at the first of the big three, which is lift. Lift is defined as how far the valve moves off the valve seat, or in other words, how far the valve opens. This illustration shows the profile of a camshaft. As I mentioned in the first video, as the camshaft turns, the lobe pushes the tappet up. The tappet moves the pushrod upward, which moves the rocker arm, and the rocker arm opens the valve. As the cam turns and the nose of the cam passes the tappet roller, valve spring pressure pushes the valve to the closed position, which pushes the rocker arm, pushrod, and tappet downward, keeping the tappet in contact with the cam lobe at all times. The distance that the cam moves the tappet and pushrod is known as cam lift or tappet lift. It's the difference between the radius of the base circle and the distance from the center line of the camshaft to the nose of the cam lobe. This is called cam lift or tappet lift. When we're designing a cam and we want to increase the lift, there are two ways of doing it. We could increase the height of the lobe, which will push the tappet farther, or we could decrease the size of the base circle, which will increase the cam lift by increasing the difference between the radius of the circle and the height of the lobe. In fact, that's what engine builders in the early days of hot rodding actually did. They would grind the heel of the cam smaller to get more lift from a stock camshaft. Crude, but effective. Okay, we've got cam lift figured out, but what about valve lift? The pushrod pushes, hence the name, one end of the rocker arm and forces it upward. The rocker arm is nothing more than a lever, and the valve side that pushes down on the valve stem is longer than the pushrod side. So the valve side of the rocker arm actually pushes the valve down farther than the cam pushes the pushrod end up. The ratio of the lengths of the valve side and the pushrod side of the rocker arm is called the rocker ratio. So if you multiply the cam lift by the rocker ratio, you'll get the theoretical valve lift. Why theoretical? Well, in the real world, the pushrods and rocker arms both flex under stress, and you will lose a small amount of the theoretical lift. This is especially true with high lift cams and heavy performance valve springs, because the increased spring force on the valve train will increase the flexing. Another factor is that at high RPM, the acceleration of the valve train components is much higher and adds even more stress to these parts. That's why S&S sells super strong chrome moly steel pushrods and high strength forged rocker arms to minimize the flexing and increase valve timing accuracy. The rocker ratio for all Harley-Davidson Evolution, Twin Cam 88, 96, and 103 engines is 1.625 to 1. The rocker ratio for Milwaukee 8 engines is 1.6 to 1. So you get over 1.5 times more lift at the valve than at the cam. Sweet. Why is lift important? Opening the valve farther allows air or exhaust to flow in or out more quickly. You get a better cylinder fill and more efficient elimination of exhaust gases. It'll be pretty easy to demonstrate this idea in the kitchen sink. When I open the valve on this faucet, water comes out. If I open it farther, water comes out faster. That's pretty intuitive, and the same principle applies to the valves in an engine. Open the valve in this cylinder head farther and the air can flow into and out of the cylinder faster because the valve presents less restriction to flow. We're most concerned about the intake valve since we only have atmospheric pressure to force the air into the cylinder. The exhaust valve is important, but exhaust gases are forced out of the cylinder by the piston, which can exert much greater pressure. It's no coincidence that the intake valve is almost always larger than the exhaust valve. Right about now, you may be thinking, yeah, give me some lift. Give me the highest lift cam they make. Not to be too much of a buzzkill, but lift does have its limits, and lift does have some downsides. First of all, just as there's a limit to how far I can open this faucet, there are physical limits on how far a valve in your engine can be opened. One of the factors limiting valve lift in your engine is the valve spring pack. It's probably easiest to demonstrate with this spring tester. As the cam opens the valve spring is compressed and exerts an opposing force which closes the valve again when the cam allows it to close. There is a limit to how far a spring can be compressed. Beyond that limit, the coils of the spring will contact each other and bind up. It's not too surprising that this condition is called coil bind. Coil bind is pretty extreme. It's the worst case scenario. Things break when this happens. The cam is trying to compress a spring that can't be compressed anymore, and something's got to give. A less apparent problem with higher lift is the fact that valve springs will fail due to metal fatigue if operated at valve lifts higher than they were designed for, even if coil bind doesn't occur. Here's another spring pack issue with high lift. We also need to make sure that the top valve spring collar doesn't come down far enough to contact the top of the valve seal. You can see when the valve opens farther, the top collar comes closer to the valve guide and seal. We have to make sure that these parts don't touch. So if you plan on running stock valve springs in your engine, you need to select a camshaft that does not exceed the maximum lift of your springs. These are called bolt-in cams. A true bolt-in cam does not require any modifications or other components for installation. Stock tappets, push rods, rocker arms, and valve springs can be reused. Cam timing is also appropriate for a stock engine. Using stock valve springs is perfectly okay for most street applications, but in addition to the limitations on lift, you can't exceed the stock rev limit. If you plan on operating the engine at a higher RPM, you should install a set of performance valve springs. In addition to allowing the use of higher lift cam grinds, performance valve springs apply more force and close the valve more quickly, ensuring that the valve follows the profile of the cam lobe and closes fully at higher RPM. Maximum lifts for bolt-in cams depend mostly on the stock valve springs in the engine. Valve springs in stock Harley-Davidson Evolution and 1999 to 2004 twin cam 88 engines can accept cams up to about 515 thousandths lift. 2005 and later twin cam 88, 96, and 103 engines can run cams of up to 585 lift with stock springs. Milwaukee 8 engines can handle lifts up to 475 lifts with stock valve springs. How come the M8 can't handle as much lift? Well, with 4 valves per cylinder, you don't need as much lift to get more air into the cylinder. Installing a bolt-in cam and using the stock valve springs can be a pretty economical upgrade. However, if you decide to install a set of high-performance valve springs, be aware that there will be some added expense, because not only will you be buying the springs, you're also going to remove the cylinder heads to install them, so labor costs are increased.